All right, let's go ahead and get started. I do see a few familiar faces here, but for those of you that don't know me, my name is Charles Sanglimsuwan. I've been working in games for some time now across many different platforms. And today, I'm a part of Unity's enterprise support team based in sunny Seattle. As a developer relations engineer, I have one of the coolest jobs in the world because I get to meet up and help developers unblock and accelerate their game development. Over the last 2 years, I've seen our developer community do some really amazing things, often though at the cost of performance. So when I first learned about Shader Graph, I got really excited by the new possibilities that it opened up. And I wanted to absolutely make sure that our most important audience, you, our users, had the right knowledge to use Shader Graph in the best way possible. We'll be covering a broad range of topics that benefits anyone interested in using Shader Graph, especially if you're in one of these roles. There is a lot of material to cover, and in case you miss anything, don't worry, we will post the slides online and the talk on YouTube shortly after Unite is over. In the next 40 minutes or so, we'll discuss how Shader Graph works, how to choose the right master node, how to optimize your Shader Graph, discuss some workflow tips, and briefly share a roadmap for 2019.1. So how many here of you have used Shader Graph before? That's a lot of you. That's great. If this is the first time you've heard of Shader Graph, you may have a few questions already, like what is Shader Graph and why? At Unity, we make no secret about our mission to democratize game development by solving hard problems to enable your success. Every game has a different look and feel and shouldn't be bound by Unity standard shaders. But we're also acutely aware that writing shaders in their native languages has a very high learning curve. We decided to tackle this problem by creating Shader Graph. Shader Graph is a tool that allows developers and artists to easily create complex and beautiful shaders that may have been out of reach previously, irrespective of whether they have an extensive background in graphics or not. By connecting individual nodes that represent different functions and values and inputs commonly used in regular shaders, you can create surface shaders to represent any kind of material. And thanks to the meticulous and granular control that users have, these output materials can range from simple effects to realistic organic matter. Out of the box, Shader Graph includes over 150 nodes with an extensive API that even allows you to create your own nodes. And even if you're a hardcore graphics programmer, Shader Graph can still be a really valuable tool to help quickly prototype your visual target or even give you a starting point to avoid writing boilerplate shader code. Early official work on Shader Graph started in about May 2017 and was released as a preview package earlier this year with Unity 2018.1. And since then, it's been downloaded almost 100,000 times, so major kudos to our preview users. With the high volume of great feedback that we received, we've been able to evolve Shader Graph fairly quickly, releasing nearly 24 updates since then. Using the latest build of Unity 2018.3, one of our top technical artists, Natalie Work, was able to create this absolutely stunning scene. She put this together using the HD render pipeline to show off what you could really do using the latest preview package of Shader Graph. Every game object that you see in this scene, including the butterfly, is actually using a shader that was authored entirely in Shader Graph. The butterfly is actually a perfect example, and if you look at it closely, you may notice how you can actually see through the wings a bit and observe how the color will gradually change based on the illumination angle. This effect is called iridescence and is actually present in many natural material surfaces. Iridescence is one of many features built right into shader graph. So clearly, shader graph is very powerful and extends the reach of artists and developers. But alas, as we're all aware, in the game development world, everything comes at a cost. And in the words of Benjamin Parker, with great power comes great responsibility. So to understand the costs associated with using shader graph and how to extract the most performance, we need to understand the foundations of how shader graph works. For shader graph to work as well as it possibly could, we needed to rely on a more modern and extensible approach to rendering. So for that reason, shader graph requires that your project use the scriptable render pipeline. There are two main render pipelines today: the high-definition render pipeline aimed at gaming PCs and high-end consoles, and the lightweight render pipeline aimed for everything else. You may have noticed another template called the VR lightweight render pipeline, but that's really just the lightweight render pipeline with VR settings enabled. So when you create a shader graph, the first node that you'll see is called the master node. The master node defines the core surface parameters and is the entry point from which shader graph will create your shader from. There's actually a few different master nodes that you can choose from, which we'll talk about in a little bit. That said, at any given time, you're only allowed to have one master node per shader. If by chance you happen to have more than one master node in your graph, only the first one that was serialized will be used. So while master nodes contain a great deal of information defining how things should look, logically, they are just a fraction of the process. To actually generate a shader that we can use in materials, we need to pass the shader graph to the render pipeline. More specifically, the graph will need to be passed into something called a shader backend, which is unique per render pipeline. Shader backends include Subshader Generators for supported master nodes. This does carry a strong implication, namely that not all master nodes are supported by every render pipeline. Furthermore, because the HD and lightweight render pipelines differ in the way they render, the same master node won't look exactly the same between these two different render pipelines. And that's because each master node actually has a different template per render pipeline, which is used by the Subshader Generator. Each template contains numerous injection points, which will vary based on the master node and the render pipeline settings. When the Subshader Generator is kicked off, your shader graph is traversed, beginning with the master node. Injection points are then replaced with actual code based on the node function and values. The process may sound a bit heavy-handed, but it's actually executed fairly quickly. Once the Subshader Generator is complete, the outcome is a shader written in the shader lab language, which is functionally very similar to HLSL or CG. At this point, the generated shader can now be used in your materials. It's important to note that this process only occurs when you're using the Unity editor and not at runtime. To better illustrate, let's go over a quick example. If you've written shaders in Unity before, this will look pretty familiar. Shaders that you normally write and those generated from shader graph both follow the same language construct. But there are a few key differences I wanted to highlight. First, properties are defined in the shader graph blackboard, and most input nodes can be converted to properties. Properties are exposed in the materials inspector and can be modified per materials instance. Next, the tag and material options are defined in the settings and various properties of the master node itself. They can be located by clicking on the gear icon on the Master Node UI. The next set of differences are perhaps the most critical. First, we need to include the various functions used in your shader graph. For example, if you use the multiply or noise function, that code will be included in your shader. Next, we need to provide the input and output data structures for the surface shaders. Unity uses this to tell the GPU exactly how data will be transferred in and out of your shader functions. The surface function itself ties all of your shader graph operations together. Let's look at a graph and see what kind of code it generates. In this shader graph, I'm simply multiplying a tangent vector with a scalar value, then setting that as input for the albedo color. The graph function that I'm using here is the multiply function. So we need to include that in our output shader. Now, for performance reasons, shader graph will only include the functions and overloads that are referenced in your graph and ultimately connect to your master node. The next thing that we need to do is to define the input and output data structures for the surface shaders. The input structure typically contains mesh data. In this particular case here, the world space tangent is a requirement and accordingly is present in the description input data structure. The output data structure has the albedo defined because it corresponds to one of the master node slots. All the other master node slots would also normally appear here, which I've omitted for the purpose of simplicity. And finally, we've reached the actual surface shader function. This is where we call the graph functions in the way that you set up in your shader graph, using data supplied from the description input data structure. At the end of the function, we simply return the calculated value in the output data structure. In this particular example, the code is doing exactly what the graph is defining, which is multiplying the tangent vector with the scalar, then setting that as the surface color. The final difference that I want to briefly mention was that we need to inject code into the vertex input and output structures, as well as the vertex and fragment shaders themselves. This is done because in order to perform operations using the mesh data, we need to pass that data along from the vertex to the fragment pipeline. This includes space transformations and other various properties depending on what the shader graph actually needs. I'll also briefly discuss hand editing shaders a little bit later in my talk, but if this was something that you're interested in, the functions that I just described now are good candidate areas to look at. So now that we understand how a shader graph works, let's use that information to our advantage. So while choosing a master node may seem like a trivial decision, it's actually an important decision that has profound implications on overall performance. Today, you have the choice to select from among 3 different master nodes: high definition lit, PBR, short for physically based rendering, or unlit. Let's go over each one of these, starting with the PBR master node. This master node works across all render pipelines, and for that reason alone, is a really great node to use if you just wanted to prototype. Furthermore, the feature set includes properties like occlusion and emission, and is broad enough for most rendering scenarios. If you lock down your render pipeline to the high definition one, then you can also consider the HD lit master node. This master node will only work on the high definition render pipeline. So while it does have a much larger feature set, it's not exactly a good choice for prototyping, since you may end up using features that aren't present in other render pipelines. Furthermore, the larger feature set can become a double-edged sword, as it may add needless complexity to your output shader code, potentially resulting in slower performance. In fact, if I just go ahead and expand that master node, you can start to imagine how complex the surface shader can really become. Using the HDLit master node for everything isn't a situation you want to put yourself in, because it becomes far too easy to, for example, enable translucency for objects that don't really benefit from that setting. Translucency and subsurface scattering, by the way, are both very expensive computationally. Later in this presentation, I'll talk about what Unity does to help in these scenarios and how it relates back to your master node selection. The last master node that you can choose from is the Unlit master node. Like the PBR node, the Unlit master node will also work across all render pipelines. It's tempting to overlook this master node because it contains a pretty bare-bones set of features. But for that reason, it's pretty lightweight and certainly has its uses. This is the master node that you want to use for effects or UI. And even though it's called Unlit, you can actually add lighting to it using a clever trick. You do this by using the provided math nodes to calculate lighting for your target shading model, which may be, for instance, Blinn Phong. All the math nodes that you need to do this are supplied in the provided node library. And once you've done the math, all you need to do is just connect the output color to the color port in the Unlit master node. This is a pretty neat and lightweight way to do some simple lighting. To summarize the master nodes available today, we suggest using PBR for prototyping due to its versatility, or if you're looking to leverage different render pipelines to target a broad spectrum of devices. And if you lock down to the HD render pipeline, you can switch over to using the HDLit master node, but only if you need it. And last, but certainly not least, don't overlook the utility of the Unlit master node, which can be useful in the right scenarios. The master node that you select and how you use the master node affects how Unity will try to optimize your shader performance. When I look at how Unity will try to optimize your output shader generated from shader graph, I like to break it down to two categories. The first one is that any feature in your master node that you don't use won't be added to your output shader. And while there are a few exceptions to this, like the albedo color, this is generally true for most features and will also depend on the render pipeline. Now, if I were to change the default value for a particular feature, that feature will get marked as active, and code for that will get added to your output shader. Moreover, connecting any node to its port will also mark that feature as active, even if the node value is identical to the default value. Let's look at the coat mask feature as an example. Now, because I left the coat mask value at 0, which happens to be the default, and there's no node connected, no coat mask code will be present in your output shader code. Now, if I were to change that to 1, or even 0.001, coat mask code would appear in your surface shader code. And tying this back to my earlier discussion point, this is precisely why choosing master nodes is especially important. When you use the HDLit master node, you have to be very careful, as you risk enabling unintended features, preventing Unity from optimizing your shader. The second category of optimization is what the shader compiler will do for you. What the shader compiler does is take your high-level shader lab code, then compile that down to low-level bytecode that can be sent over to the GPU. Moreover, this doesn't apply just to shader graph output, but to all shaders that go through Unity's shader compiler. And as part of the bytecode generation process, the shader compiler will also attempt to optimize your shader code, typically by removing no-op code. And as it turns out, a lot of the rules for the first category completely carry over. For example, let's look at the metallic feature, which is present on both the PBR and HDLit master nodes. So if we leave the default value to 0 and have no additional nodes connected to its port, that code block will be compiled out completely by the shader compiler, which you can independently verify by looking at the output shader bytecode. Another example is emissions, which is a little bit more nuanced. In the case of emissions, you have 3 requirements. First, the color must be left at the default value of black. Next, it must be left unconnected to any other node. And third, the emissions property must be disabled in the material. If all 3 requirements are met, emissions code will be compiled out in your shader code. To reiterate, taking full advantage of the Unity shader generation process requires that you first don't change the default values unless you need to, and likewise, don't connect nodes unless they're required. These categories of optimizations that I've discussed thus far have been confined to the shader code itself. But what's more critical is how these shaders are used within the context of your draw calls. Ideally, you want to reduce the number of draw calls that your game submits to reduce the frequency of costly GPU state changes to improve overall rendering performance. One of the best ways to do this is by leveraging GPU instancing, which is supported on most modern GPU hardware. Compared to static batching, GPU instancing has the advantage of not requiring geometry replication data. Now, typically, when you write shaders on your own, you have to add specific code to enable GPU instancing in your shaders. All shaders created from Shader Graph will support GPU instancing out of the box. You do need to explicitly enable this in your material, and it does increase the size of your materials by a tiny bit. Something to also note is that, like static batching, GPU instancing does not work on your skin mesh renderers. Moreover, dynamic batching is disabled in the scriptable render pipeline. And even if it did work, dynamic batching limits you to no more than 900 vertex attributes per mesh, which wouldn't really work for most modern 3D games today anyway. Beginning in Unity 2018.3, your skin mesh renders can instead make use of a new feature called the SRP Batcher. The SRP Batcher effectively replaces dynamic batching in the scriptable render pipeline and will work on both mesh renders as well as skin mesh renderers. If you're writing shaders by hand and you want your mesh to be picked and batched by the SRP Batcher, it does require that your shader write out per material parameters in a dedicated constant buffer. It's not exactly a trivial amount of work, but the results can be quite drastic. Using the SRP Batcher, we've seen rendering speeds increase anywhere from 27% to over 400% in our internal tests, as noted in this chart comparing rendering times, which includes the cost of shadow passes. And to clarify, since this chart is measuring time, lower is better. Where the SRP Batcher really shines is when you have a single shader, like an Uber shader, used across a lot of materials. You'll still likely see performance benefits if you only have one shader per material, though it won't be as pronounced. Every shader created using Shader Graph will automatically support the SRP Batcher to take full advantage of these performance benefits. So up to this very moment, we've talked a lot about master nodes and what Unity does to help your game run as fast as possible. What we'll be focusing to next is what you can do to make your shaders perform even faster. The absolute first step is to understand what your performance is bound by. If you're bound by the CPU, then optimizing your shaders won't increase your frame rate, though it might improve your battery performance if you're on mobile. If you know that you're bound by the GPU, the next step is to understand what specific part of the graphics pipeline you're bound by. To do this, you'll need to use the graphics profilers native to your target platform, because the Unity frame debugger doesn't include timing information. This is critical because it affects the way we need to approach optimization. Optimizing for memory-bound situations is going to be different than optimizing for vertex-bound scenarios. Earlier, I shared how shader graph works by traversing nodes in your graph, then injecting shader code when needed. So for that very reason, you typically want to reduce the number of nodes as much as you possibly can in your graph. And doing so will reduce your shader complexity. The node decimation process is achieved through a few different ways. They include eliminating no-op nodes, like multiplying values by 1. And if you know that you're not bound by texture fetches, another clever way to reduce nodes is by baking values back into the textures themselves. This is a particularly useful alternative to, say, expensive noise functions. Let's take this example, where what I'm doing here is sampling a texture, then multiplying the color channels by a scalar to increase its brightness. This is absolutely fine for prototyping, but when you're ready to start optimizing, you can simply increase the brightness of the base texture, then remove the multiply node altogether to reduce your math operations per frame. Keep in mind that this optimization would only help your performance if it were bound by ALU. And while there are a few cases where having more nodes is actually preferable, for most scenarios, combining nodes is a great strategy to aim for. Let's go ahead and look at another detailed example. The light fall-off effect that you see here, or certain glass-like surfaces, is achieved through a few different ways. A really common way to do this is by calling the power function multiple times in succession. Here's what the shader graph for that shader looks like. It might be a bit hard to see, but try to draw your attention to these adjacent power nodes. Let's zoom in a bit. Now, to alleviate this, we can use the laws of mathematics to combine the 4 power nodes into a single one. And the visual look and feel is completely identical. And again, if you know that you're not bound by texture fetches, then an even better approach to this would be to bake the fall values into a texture, then sample the texture when you need it. If you are bound by texture fetches, then sampling the texture in this case may end up hurting your performance. And this is precisely why profiling is very important. So in addition to reducing nodes themselves, you'll also want to look at each node in itself. Basically, use just what you need. If you only need a vector 2, don't use a vector 4, and you'll save 8 bytes of shader memory. Each node does have a theoretical memory cost, and since you can see all the shader code generated, it becomes fairly easy to calculate the memory cost of the nodes that you're using. And overall, reducing your shader memory cost will help in GPU bandwidth situations. For those of you wishing to take this even further, you can switch to a less precise format for improved shader performance. This is especially helpful if you're targeting mobile devices. It does require some code modification. Thankfully, Shader Graph is fully open source on GitHub, And there's a few different ways to approach this, each with varying degrees of involvement. In the near future, we'll add half precision support, but if you want to get a head start right now, this is the class and enumeration that you want to start exploring. If you've been writing shaders for some time now, this isn't new to you. Something to keep in mind is that all the other shader best practices that you learned about completely carry over to shader graph. Such best practices include reducing your math operations, which really ties back to node decimation. First, look to combine your scalar values before applying them to vector values. Doing so will reduce the math that your shader needs to perform. Next, instead of branching, which is actually quite expensive to do on all GPUs, prefer to blend the results in your graph instead. Additionally, you'll want to spend some time to research the impact of certain math operations on your target platform. For example, if you look at the reciprocal function, there's actually two different modes, default and fast. Using fast requires shader model 5, which isn't universally supported on all hardware. So you can stand to benefit from switching to fast mode if you know that all of your target platforms properly support shader model 5. Another general example are color masks, which tend to perform inefficiently on PowerVR and other mobile chipsets. The last point that I want to make here is to prefer constants whenever possible. In the context of shader graph, this refers to inline nodes. As I said earlier, many input nodes can be converted to a property in shader graph, exposing them in the materials inspector. Properties make it really convenient to prototype how your shader will look on actual game objects. But do be aware that converting a node to a property eliminates the possibility for the shader compiler to optimize your shader function. So while it's perfectly fine to use properties for prototyping, we do strongly recommend converting them back to inline nodes when you're out of the prototyping phase, allowing for the shader compiler to generate better optimized code. If you're a seasoned graphics veteran, you may be interested in optimizing the generated shaders by hand. You'll have to be aware that this is a one-way path, and there's no way to carry back any manual optimizations that you make. The reason for this is because these manual optimizations would likely interfere with the injection-based templated approach that shader graph uses. But if you're interested in doing this anyway, it's a straightforward process. All you need to do is right-click the master node, select copy shader code, then paste that to a new shader file. And once you've made your desired changes, don't forget to change your material to use the right shader. And because this is a one-way path, we strongly recommend reserving this manual optimization step towards the end of your development lifecycle. The last tip that I want to give isn't so much for runtime performance, but for your own sanity. As you're building your shader graph and it starts to get larger in size, you may start to notice UI slowdowns. And that's because every node that eventually connects to the master node is continually evaluated. Conversely, nodes that are disconnected from the master node aren't actually evaluated and won't be included in your generated shader. So it's completely safe to leave those in for prototyping. Now, if you want to quickly edit a lot of nodes in succession, you can instead connect them to a preview node that itself isn't attached to the master node to help save you some time. To summarize the entire end-to-end workflow of using shader graph, from the onset, we suggest prototyping with the PBR Master Node and only move to HDLit if necessary and appropriate. You'll also want to think about your approach to shaders, whether you want to go with Uber shaders or not, to take full advantage of the SRP Batcher. And when you no longer need to prototype and you're ready to start optimizing, begin with aggressively reducing your nodes. And if properties are no longer needed, don't forget to convert them back to inline values, allowing them to be potentially optimized by the shader compiler. And finally, when you're near the end of your project, that's a good point to start hand optimizing your shaders. As we approach the end of my talk, I want to conclude with a few exploratory ideas that you can pursue using Shader Graph. The first of which is the Node API, which allows you to create your own custom nodes. This is particularly useful for doing a number of things, like, say, custom lighting, perhaps half-precision support, or even a specialized noise function that we don't yet offer. We've gotten lots of excellent feedback from our preview users, so expect this to quickly evolve until Unity 2019.1. As most Unity games are bound by CPU performance, I'd also encourage developers to start exploring greater inclusions of Vertex animations in their titles. Compared to animators, Vertex animations have a relatively low impact on your CPU performance, as most of the work is done on the GPU. Good candidates for this include the subtle movements of foliage, water animations, or perhaps cloth effects. Let's look at a few examples that we've crafted internally. The movements of this tree follow an algorithm pioneered by Tiago Souza. And if you observe carefully, you may notice different phases for the trunk, branch, and leaves. All of this is completely driven by Vertex animations, timed by varied sine wave values, and also completely authored in Shader Graph. We posted this to a blog about 2 weeks ago, but this example here showcases using Shader Graph to create Vertex displacement effects to simulate the movement of water. The flags animations in the middle of the island are also driven by Vertex animations and is also authored in Shader Graph. Shader Graph has certainly come a long way from its inception, but we're not stopping there. Beginning in Unity 2019.1, we will launch the first official verified release of Shader Graph. Coming out of preview and becoming a verified release means Shader Graph will undergo a highly rigorous testing process to ensure a high-quality, stable feature release, which we understand is very important for everyone here. And based on your feedback, the Node API will receive an extensive upgrade, allowing you to do even more. And of course, you'll also find key quality of life improvements across the board. When you go and download Shader Graph tonight, remember that we have a lot of resources out there to teach you how to use Shader Graph to create amazing effects. You can also check out the impressive samples from our very own evangelism team to get a better idea of what you can really do. And with that, we've arrived at the end of my talk today, and now I'd like to open up the floor to take any questions.
Hey.
Yes.
So if we're releasing a game by the end of this year, we've got an Amplify workflow at the moment for using shaders, and we're looking at using the lightweight scriptable random pipeline for that. Should we do that, or should we switch to Shader Graph? You said there's a lot of optimizations that are going to be happening in 2019.1. What do you suggest?
So the question was, I'm using a lightweight render pipeline today, and I'm currently using Amplify. Should we use Shader Graph?
Correct.
The answer to that is a bit nuanced. It really depends on your release date. If you're looking to release soon, I would suggest continue using Amplify. It's a great tool. If you're looking to release next year, I think that's a great time to go ahead and start exploring shader graph. I do think it's worth trying out right now to just, since you're already familiar with Amplify, it's a great opportunity for you to try out shader graph, give us feedback on what you think is missing, and we'll continue to evolve shader graph to meet your needs.
Thank you.
I had a question about the foliage and water animations that you were talking about with the Vertex animations. Are those examples going to be available built into it, or like someplace online where we can download, see how they work, and utilize something like that?
The question was, will the sample and water animation effects, will those samples for that be posted online? The answer is yes. If you actually go to our blog, we do post samples for both the foliage and water examples on our blog, which you can download, and it's completely open source. Feel free to take at it and give it a shot.
All right, thanks.
Sure thing.
Hi, I was wondering if shaders made in Shader Graph can be used in older versions of Unity?
The question was, will shaders made in Shader Graph work in other versions of Unity? It actually depends on the render pipeline. So as long as, in most cases it will work, there are a few cases where, depending on which render pipeline, it may not work there. So beginning with Unity 2019.1, you can expect a lot more stability in that regard. Historically, because we've been iterating very quickly, there may be some breakage between these different versions of the render pipeline and the shaders that you create in Shader Graph. Thankfully, because of the templated approach that we use, in most cases, all you need to do is just load up your graph in Shader Graph with the target render pipeline, and if you typically just resave out the shader, it should generally work.
Oh, so like copying the code and then pasting it in another file?
If you open up the graph file, it's actually a JSON file, but you can double click it and it should just open up in Shader Graph.
Got it. Cool.
Yeah.
Thank you.
Sure thing.
I assume, just having used other node-based shaders tools, that we'll be able to sort of write custom input nodes, but will we be able to also write custom master nodes, for example, if we want to have a custom lighting solution?
The question is, will we be able to write a custom master node? At the moment, no, but it's something we're really exploring for future release.
Cool, thank you.
Hi. The question is, will you increase example library to see more power of shader graph, like templates, examples?
The question was, will we provide a library to provide some examples or templates? So if you go to this link over here, if you check out Andy Touch's blog, you can just search on Google, Andy Touch, shader graph. He has a ton of amazing examples out there that teach you how to do things like cell colors, rim lighting, cell shading, displacement effects. Keijiro's blog is also a great source for that.
Yeah, I saw that a lot, cool stuff, but maybe you can do more.
We will continue to add more samples to this, just because we really do believe in the possibilities it opens up. But we also want to illustrate good examples of how to use shader graph and what you can really do. So do expect that library to grow.
Okay, thanks.
Sure thing.
Hey, I was wondering if you could go into why non-default values can't be optimized away.
The question was, why can't non-default values be optimized away? A lot of that has to do with the shader compiler that we actually use. We actually use the D3D shader compiler, which we then compile out to other platforms using an open source project called HLSLCC. So we don't actually control the shader compiler itself. But that being said, we are definitely exploring how can we even better optimize your shaders.
Okay, thank you.
Yeah.
I was wondering, you were saying that in certain instances it would make sense to create another texture instead of performing math operations. And I was wondering if it would be possible for you to integrate some system that would allow you to, let's say, print the texture.
So the question was, will we add a feature that allows us to go ahead and print out a texture, save out texture, based on your node values to that you can reference sample later, right?
Either as a lookup table or directly as the replacement sample replacement texture.
What's funny was, as I was giving this presentation internally to our technical artists, they asked for the same exact feature. So it is certainly that we're looking at, and we will put on a roadmap. So that being said, we're actually out of time. So what I'll do is I'll stand outside and I'll answer Q&A there. Thanks, everyone.